The topic of this video is C13 NMR intensity, and I pointedly did not say integration, and that is because if you've watched the C13 multiplicity video, we do things in collecting the spectra that make it impossible to integrate well. We're altering the spectra in ways that make integration untrustworthy. But nevertheless, it's still a valuable concept to be able to say, okay, how many carbons are in this environment? And there is still that information contained within the spectrum to some extent. It's just disguised a little bit. So anyway, it's kind of like integration, but not. You cannot integrate a C13 spectrum, but you can learn things from the intensity of the various peaks in there. And specifically, you can learn how many carbons are in a given environment in the molecule. Now, again, much like proton NMR, one of the main values of a C13 spectra is simply learning how many carbons there are overall. And there's two parts to that. How many environments are there, and how many carbons are there
in each environment.
And so this molecule right here is, of course, benzene, and it has a single type of carbon in it. And of course, benzene has a resonance structure wherein we have moved all of the double bonds slightly over, and therefore what we have now are these double bonds instead. And so this is a resonance form. The red arrows move you to this structure. The yellow arrows would move you back. And so benzene doesn't look like either one of these. In reality, of course, and I've shown you this before, benzene looks like the superposition of both. In other words, it can be drawn as having this slight double bond character all the way around, or alternatively, the way it shows up in some texts is to draw it this way, with essentially a ring current of electrons. But all of this is a long way of saying that when I draw all of these benzene structures, and I will draw several more, you should immediately think of them as having all the same kinds of carbons because the double bonds are not fixed. They are instead smeared across the entire thing. So the resonance hybrid smears that electron density everywhere. So every single one of these carbons is going to be identical. Therefore, if I'm looking at benzene, how many types of carbon does it have? It has one, and it can't be integrated, but if you did integrate it, it would be worth 6 carbons. Okay, so why do I bring that up? Well, because as soon as you disrupt the symmetry in the molecule by, say, putting a methyl group on it, so now you have toluene instead of benzene, what that does is change how many environments are in the molecule. So here, all of the carbons were identical. Here, by attaching a carbon right there, what we have done is now split the molecule in some sense and desymmetrized it. Although, of course, because of this resonance, you still have a plane of symmetry that runs smack down the middle of it. Okay, so how many unique carbon environments are there in this molecule? Well, there's one right there. There's 2 right there. Those are clearly different from each other. Then these 2 are the same because of the symmetry. These 2 are the same because of the symmetry. And now we have a 5th. So here we had 6 carbons, all in the same environment. Here we have 7 carbons, but they're split into 5 different environments. Okay, now I've made 2 alterations to the scheme, and one is that I color-coded each of the environments so that I could put them onto this chemical shift axis. And the other thing I've done, of course, is erase the benzene and put the chemical shift axis here. And what I'm doing is showing between 0 and 100, there's not much of interest except for the CDCl3, which is not part of the molecule, so you can ignore it. Again, the 3-line pattern you can always ignore. But then all of the interesting stuff in this molecule is really going to show up in this 100 to 150 range. This lone methyl out here, you'd expect to be right around, oh, I don't know, 20 or so. Let's put it there arbitrarily. But let's now try to situate these. Now, because this particular carbon has more stuff around it than anything else, he'll show up probably the furthest left of everything. So I'll go ahead and arbitrarily put him here. And I'm totally making these numbers up. But I know that he's definitely going to show up in the 100 to 150 range because of carbon chemical shift. On a benzene ring, on an sp2 carbon, he'll be in there, but I'll put him leftmost of all these other peaks. Now comes the more tricky part. So let's arbitrarily put this guy in somewhere, and he's going to be further right than position 2, so position 5 is going to be over here somewhere. And I very carefully made him taller than the pink one. And this is going to show up for complicated reasons, dealing mostly with multiplicity. So if you haven't watched the C13 multiplicity video, this would be a good time to go take a peek. All right, these 2, however, are definitely going to show up as being taller than this one, and that is because there are 2 of them and one out of him. So I'm going to make him about twice as tall as this guy. And that was sort of an arbitrary guess as well. And the same thing with these, they should be about the same height. And so my guess for the C13 spectra for toluene would be something like that. This specific one has hydrogens associated with it. So given the way we choose to run the C13 spectrum, it will have a certain height because it's one carbon and a hydrogen attached. Position 5, likewise, is a carbon, single carbon, that has hydrogens attached, and it will be affected in similar ways to position 1. So I would expect those two heights to be the same. These positions, however, 3, which has 2 carbons in that environment, and 4, which has 2 carbons in that environment, you'd expect to show up as substantially taller and probably twice as tall. But you cannot integrate C13 NMR, so it won't bother me if it's not really twice as tall, if it's just taller. But in practice, often it is twice as tall, it's just you can't trust that. So if I see a peak that's twice as tall, my first thought is maybe there are 2 carbons in that environment. It doesn't have to be true. In fact, it may be misleading, but that would be my instinct. If I see a peak that's twice as tall, I think, wow, there's probably 2 carbons there. Now, if I see a peak that's 3 times as tall, it might be 2 times 2 carbons in there, might be 3 carbons in there. Again, you can't trust it, you can't integrate it. But if you see a peak that's extra tall, you should think there are more in that environment. Okay, so these two should be the same, really, although it wouldn't bother me if they were a little different from each other. And then the thing that's different is any carbon that doesn't have a hydrogen attached is going to show up as smaller than it should. So this is what a height of 1 looks like in this spectrum. This right here is what a height of 1 looks like that does not have a hydrogen attached. A quaternary carbon, for NMR purposes, is a carbon that only has carbons bound to it, not hydrogens, will show up as extra small, again, because of the way we choose to run the spectrum. So big picture, this would be what I would expect. And again, peak height is not exactly integration, but it's a lot like integration.
And so now we're looking at a spectrum of toluene, and unlike normal, I didn't take this in CDCl3, so there's no triplet here at 77.16. Instead, this is in DMSO D6, so that's the solvent peak right there. And you can tell that by the regular multiplicity in the C13 NMR, which is usually a strong sign that you are looking at deuterium. Here's the peak around 20, that's the methyl, and now over here are the 4 peaks in the aromatic region. So how did I do? Pretty well, I'd say. These two are not exactly the same height, but they're pretty tall. They're not exactly twice as tall as this guy, but again, they're substantially taller. And this one are not exactly the same height, but they're not that different from each other. The methyl is about half as tall as these guys as well. And then, of course, the thing I was just pointing out is that the methyl and this CH1, both of which have H's on them, are going to be substantially taller in the C13 NMR than the quaternary, which shows up as unusually small. And again, that's a function of the way we choose to run the C13 NMR spectra, and you can look at the multiplicity video if you'd like more insight into why that might be the case. This is, in fact, kind of how intensity works in C13 NMR. It's a decent proxy for integration, but you could tell that if I did the integrals, it wouldn't work as well as I'd like. And just to prove my point about the integration, I've done the integration now, and if I integrate the quaternary carbon as 1, then these end up as 3 times bigger and 2.5 times bigger, and these are 6 times bigger, and so on. Again, integration in C13 is nonsense, but intensity is a decent proxy for integration, and if you're looking at intensity, you would conclude that these two are the same height, and these two are quite a bit taller, and then to my eyes, this is pretty clearly a quaternary, but it also could be the case that this is 1, these are twice as tall as that guy, and these are twice as tall as that. So you're going to always have to do some interpreting. So the most basic level of C13 interpretation is that there are in fact 5 carbons in the spectra. A better level of interpretation is that these two are half as tall as these two, and then maybe that we have a quaternary. But it's not out of the question that we have 5 carbons. It's not out of the question that we have 7 carbons. 1, 1, 2, 2, 1. And it's also not out of the question that we have 1, 2, another 2, 4, and another 4. All of those are plausible, at least based on this spectrum, and you would need to know more information like how many hydrogens are in the molecule in order to reach a firm conclusion.